Hello everyone. So in this video we are going to discuss about the Fourier series representation of a very common signal, and that is periodic square wave. So we will discuss about the Fourier series representation of periodic square wave. We are going to discuss this specific kind of signal just because it is very widely used in the field of signal and systems. So we should know its Fourier series representation. So let's first define about periodic square wave. So the definition of periodic square wave is that xt is equals to 1 when mod of t is less than t1, and it will be 0 if mod of t1 lies between a value of t1 and t by 2. And for this signal it is periodic with period t. So the signal is periodic with period t, and fundamental frequency will be omega naught is equals to 2 pi by t. So this is your fundamental frequency. So let's have a graphical representation of this signal to understand it better. So this is the definition. From this definition we can plot the graph as, so this will be your time axis, and here for an interval of minus t1 to t1 the signal value will be 1, and for the interval t1 to capital T by 2, so here it is the interval t1 to capital T by 2, the value will be 0, and similarly from minus t1 to minus t by 2 the value will be 0. And since this function is periodic with period t, so it will repeat it after a period of t. So if this is 0, this will be your t and this will be your minus t, and the function will repeat itself. The same signal will be seen after a period of t, similarly for the axis of minus t, and it will repeat further for 2t and minus 2t, 3t and minus 3t, and so on. So in this manner it is a repetitive and periodic function. So this is your basic representation of this signal. So this is your x of t. So to get a Fourier series we have to first get an interval of integration. So because of symmetry we will choose an interval of minus t by 2 to t by 2. So this will be the interval of integration. So this will be the interval of integration. So we'll choose a t which is varying from minus t by 2 to t by 2. But we can choose any such interval. The only condition is that we have to choose an interval of length capital T. So we can choose any, like you can do it for 0 to t also, 0 to minus t also, or any such interval whichever you want to take. So the next thing is that we will have to get the coefficients for the Fourier series. So we know the formula, we have already derived the formula in the previous video. So we know that an, that is coefficient, will be equal to 1 upon t integration over a period of t x of t e raised to the power minus jk omega naught t dt. Now we will first get the value of a of 0, that will be equal to 1 by t. Now the interval we know that it's varying from minus t1 to t1, and in this interval the value is 1, for other interval it is 0. So we are just taking the value from minus t1 to t1, and that will be dt, and this value will be equal to 2 t1 by t. And this a naught is basically what? It's the average value or DC value you can say. So it is an average value of xt. This is also called the DC value. So now we have the expression for the coefficient for k is equals to 0, and next we will see the coefficients when k is not equal to 0. So from the representation, what we can do, we can take ak as 1 upon t minus t1 to t1, that is the interval, and that value is 1. So you will take 1 into e raised to the power jk omega naught t dt, and this value we know from the integration property that it will be equal to 1 by jk omega naught t e raised to the power minus jk omega naught t, and the limit will be from minus t1 to t1. Now we'll replace this interval, so we'll get ak as 2 by k omega naught t so it will be k omega naught t, and the value will be e raised to the power jk omega naught t1 minus e raised to the power minus jk omega naught t1. This will be divided by 2j. We have done some rearrangement also, so that it will come into a special form. As you can easily see that this is the form for sine function. So what we will get finally by rearranging, we get 2 sine k omega naught t1 by k omega naught t, and this value came just because we have replaced the value of e raised to the power jk omega naught t1 minus e raised to the power minus jk omega naught t1 by 2j, this value as sine of that function. So now we know that omega naught t is 2 pi, because omega naught was 2 pi by t. So this will implies that our ak will be equal to sine of k omega naught t1 by k pi. So this is your final representation for k not equal to 0. So we got two expression, one for ak for k not equal to 0, and other is for a naught, that for which k is equals to 0. Now to see the representation, or that like how this series look like, so we will take a value of t. So suppose we take a value of t as 4 of t1. So what this represent, when we take t is equals to 4 of t1, so t1 will be capital T by 4. So this value in the graph, this will be equal to t by 4. So minus t by 4 to t by 4, it will be a wave of unity, and then it will be 0. So what it means that xt will be a wave with unity for half period, and it will be 0 for other half. So now we can directly replace your value of t1 in this ak expression, which we have already deduced. So what we will get? We will get an ak of sine pi k by 2 by k pi for k not equal to 0, and it will be equal to 1 by 2 when k is equals to 0. So from this expression, what we can write? We can write different coefficients as, so a of minus 1 is equals to a of 1, which will be equal to 1 by pi. Similarly, a of minus 3 is equals to a of 3, which is equals to minus 1 by 3 pi, and a of 5 should be equal to a of minus 5, that will be equal to 1 upon 5 pi. So you can see here 2-3 properties, that as the value of k is increasing, the value magnitude of the coefficients is decreasing. Also the even terms is 0, just because the sine function will be 0 for even values of k, and the third term is that there will be alternate change in the sign. So it is positive value, then it is negative, and then positive, then negative, like that it will happen. So let's plot to see how the Fourier series is distributed. Fourier series coefficients is distributed along the axis. So the plot will be, so as we know, for k value of 0, what will be the value? It will be 1 by 2. So it is the largest value. Then for minus 1 and 1, the value is 1 upon pi. Similarly for minus 2, and 2, it will be a value of minus 1 by 3 pi. So, it will be less value, but the sign will be different. Similarly, for minus 5 and 5, the value is further reduced, but the value will be positive, and so on, like it will be having similar values. So, this is the different value of k for which we get the ak value. And now, what is the special? The coefficients are regularly spaced sample of the envelope. So, what will be the envelope will define that function 2 sin omega t1 by omega that we have seen. So, this is the envelope of that signal. So, the coefficients are regularly spaced samples of the envelope, that is 2 sin omega t1 by omega. So, this is omega, and you can verify it further that as we increase the t value and the spacing between the sample will decrease. So, as the t value will increase, the spacing between the coefficients will decrease further. So, this can be verified by taking different values of like t. Here we take 4 t1, you can take some 8 t1, 16 t1, and see that the spacing will further reduce between the sample. So, this is very basic derivation for the Fourier series coefficient of a very common signal, which is your like periodic square wave, and this will come very frequently as we move further in this topic. So, thank you.